Yeah. Okay, 4, 3, 2, 1. Okay, I see you guys are in a happy mood. I don't know if that means 1806 is ending or the quiz was good. My birthday conference was going on at the time of the quiz, so in the conference, of course, everybody had to say nice things, but I was wondering what would my 1806 class be saying, because it was at exactly the same time. But what I know from the grades so far, they're basically close to and maybe slightly above the grades that you got on quiz 2. So very satisfactory. And then we have a final exam coming up. And today's lecture, as I told you by email, will be a first step in the review, and then on Wednesday I'll do all I can in reviewing the whole course. So, but the best, so my topic today is actually, this is a lecture I've never given before in this kind of in this way, and it will, well, 4 subspaces. That's certainly fundamental, and you know that. So I want to speak about left inverses and right inverses, and then something called pseudo-inverses. And pseudo-inverses, let me say right away, that comes in near the end of chapter 7, and that would not be expected on the final. But you'll see that what I'm talking about is really the basic stuff that for an m by n matrix of rank R. We're going back to the most fundamental picture in linear algebra. Nobody could forget that picture, right? When you're my age even, you'll remember. The row space and the null space, orthogonal complements over there, the column space and the null space of A transpose column, orthogonal complements over here. And I want to speak about inverses. Okay. And I want to identify the different possibilities. So first of all, when does a matrix have just a perfect inverse, two-sided, you know, so the two-sided inverse is what we just call inverse, right? And so that means that there's a matrix that produces the identity, whether we write it on the left or on the right. And just tell me, how are the numbers R, the rank, N, the number of columns, M, the number of rows, how are those numbers related when we have an invertible matrix? So this is the matrix, which was, chapter 2 was all about matrices like this, the beginning of the course. What was the relation of R, M, and N for the nice case? They're all the same, all equal. So this is the case when R equals M equals N. Square matrix, full rank, period. Just so I'll use the words full rank. Okay, good. Everybody knows that. Okay. Then chapter 3. We began to deal with matrices that were not of full rank. When they could have any rank, and we learned what the rank was. And then we focused, if you remember, on some cases like full column rank. Now, can you remember what was the deal with full column rank? So now this is going to be the case. I think this is the case in which we have a left inverse, and I'll try to find it. So we have but what was the situation there? So that it's the case of full column rank, and that means, what does that mean about R? It equals what's the deal with R now? If we have full column rank, I mean the columns are independent, but maybe not the rows. So what is R equal to in this case? n, thanks, n. R equals n. The n columns are independent, but probably we have more rows. What's the picture, and then what's the null space for this? So the n columns are independent. What's the null space in this case? So, of course, you know what I'm asking. You're saying, why is this guy asking something? I know that, I think about in my sleep, right? So the null space of this matrix, if the rank is n, the null space is, what vectors are in the null space? Just the 0 vector. Right? The columns are independent columns. No combination of the columns gives 0 except that one. And what's my picture over let me redraw my picture. My picture is I have the row space is everything. The row space is all of, no, is that right? The row space, let's see, I often get these turned around, right? So what's the deal? The rank, the columns are independent, right? So the rank should be the full number of columns. So what does that tell us? There's no null space, right? Okay, the row space is the whole thing. Yeah, I won't even draw the picture. So, and what was the deal with, and these were very important in least squares problems. Because, so what was the, what more is true here? If we have full column rank, the null space is 0. We have independent columns. The unique, so we have 0 or 1 solutions to AX equal B. There may not be any solutions, but if there's a solution, there's only one solution. Because other solutions are found by adding on stuff from the null space, and there's nobody there to add on. So the particular solution is the solution, if there is a particular solution. Of course, the rows might not be, probably not independent, and therefore some right-hand sides won't end up with a 0 equals 0 after elimination. So sometimes we may have no solution or one solution. Okay. And what I want to say is that for this matrix A, yeah, tell me something about A transpose A in this case. So this whole part of the board now is devoted to this case. What's the deal with A transpose A? I've emphasized over and over how important that combination is. For a rectangular matrix, A transpose A is the good thing to look at. And if the rank is n, if the null space has only 0 in it, then the same is true of A transpose A. That's the beautiful fact. That if the rank of A is n, well, we know this will be an n by n symmetric matrix, and it will be full rank. So this is invertible. This matrix is invertible. That matrix is invertible. And now I want to show you that A itself has a one-sided inverse. Here it is. The inverse of that which exists times A transpose. There is a one-sided, there is a, shall I call it A inverse left of the matrix A. Why do I say that? Because if I multiply this guy by A, what do I get? What does that multiplication give? Of course, you know it instantly. Because I just put the parentheses there. I have A transpose A inverse times A transpose A, so of course it's the identity. So it's a left inverse. And so we have, and this was the totally crucial case for least squares. Because you remember that least squares, the central equation of least squares had this matrix A transpose A as its coefficient matrix. And in the case of full column rank, that matrix is invertible, and we're go. So that's the case where there is a left inverse. So A does whatever it does. We can find a matrix that brings it back to the identity. Now, is it true that in the other order, so A inverse left times A is the identity? Right? This matrix is M by N. This matrix is N by M. The identity matrix is N by N. All good. All good if you're N. But if you tried to put that matrix on the other side, it would fail. If the full column rank, if this is smaller than M, the case where they're equal is the beautiful case, where that's all set. Now we're looking at the case where the columns are independent, but the rows are not. So this is invertible, but what matrix is not invertible? A transpose is bad for this case. A transpose A is good. So we can multiply on the left, everything good, we get the left inverse. But it would not be a two-sided inverse. A rectangular matrix can't have a two-sided inverse, because there's got to be some null space, right? If I have a matrix that's rectangular, then either that matrix or its transpose has some null space. Because if N and M are different, then there's going to be some free variables around, and we'll have some null space in that direction. Okay, tell me the corresponding picture for the opposite case. So now I'm going to ask you about right inverses. A right inverse. And you can fill this all out. This is going to be the case of full row rank. And then the R is equal to M now. The M rows are independent, but the columns are not. So what's the deal on that? Well, just exactly the flip of this one. The null space of A transpose contains only 0, because there are no combinations of the rows that give the 0 row. We have independent rows. And in a minute, let's give an example of all these. How many solutions to AX equal B in this case? The rows are independent. So we can always solve AX equal B. Elimination never produces a 0 row, so we never get into that 0 equal 1 problem. So AX equal B always has a solution, but too many. So it's probably, there'll be some null space. The null space of A, what will be the dimension of of A's null space? How many free variables have we got? How many special solutions in that null space have we got? So how many free variables in this setup? We got n columns, so n variables. And this tells us how many are pivot variables. That tells us how many pivots there are. So there are n minus m free variables. So there are infinitely many solutions to AX equal B. We have n minus m free variables in this case. Okay. Now I wanted to ask about this idea of a right inverse. Okay, so I'm going to have a matrix A, my matrix A, and now there's going to be some inverse on the right that will give the identity matrix. So it'll be A times A inverse on the right will be I. And can you tell me what, just by comparing with what we had up there, what will be the right inverse we even have a formula for? There will be actually there are other left inverses, that's our favorite. There will be other right inverses, but tell me our favorite here. What's the nice right inverse? The nice right inverse will be, well, there we had A transpose A was good. Now it'll be A transpose that's good. So the good matrix, the thing we can invert is A transpose. So now if I just do it that way, there sits the right inverse. You see how completely parallel it is to the one above. Right. So that's the right inverse. So that's the case when there's, in terms of this picture, tell me what the null spaces are like so far for these three cases. What about case 1, where we had a two-sided inverse, full rank, everything great? The null spaces were like gone, right? The null spaces were just the zero vectors. Then I took case 2. This null space was gone. Case 3, this null space was gone. And then case 4 is like the most general case when this picture is all there. When the null spaces, this has dimension r, of course. This has dimension n minus r. This has dimension r. This has dimension m minus r. And the final case will be when this when r is smaller than m and n. But can I, just before I leave here, look a little more moment at this one, at this case of full column rank. So A inverse on the left, it has this left inverse to give the identity. I said if we multiply them in the other order, we wouldn't get the identity. But then I just realized that I should ask you, what do we get? So if I put them in the other order, so if I continue this down below, but I write A times A inverse left, so there's A times the left inverse, but it's not on the left anymore. So it's not going to come out perfectly. But everybody in this room ought to recognize that matrix, right? Let's see, is that the guy we know? Am I okay here? What is that matrix? P, thanks, P. That matrix, it's a projection. It's the projection onto the column space. It's trying to be the identity matrix, right? That's a projection matrix is it tries to be the identity matrix, but you've given it an impossible job. So it's the identity matrix where it can be, and elsewhere it's the zero matrix. So this is P, right? The projection onto the column space. Okay, and if I asked you this one and put these in the opposite order, so this came from up here. And similarly, if I tried to put the right inverse on the left, so that like came from above. This coming from this side, what happens if I try to put the right inverse on the left? Then I would have A transpose inverse A. If this matrix is now on the left, what do you figure that matrix is? It's going to be a projection too, right? It looks very much like this guy, except the only difference is A and A transpose have been reversed. So this is a projection. This is another projection onto the row space. Again, it's trying to be the identity, but there's only so much the matrix can do. And this is the projection onto the column space. So let me now go back to the main picture and tell you about the general case, the pseudo-inverse. So these are cases we know. So this was important review. You've got to know these business about these ranks and the free variables. Really, this is linear algebra coming together. Yeah, and you know, it's one nice thing about teaching 1806. It's not trivial, but it's, I don't know, somehow it's nice when it comes out right. I mean, well, I shouldn't say anything bad about calculus, but I will. I mean, like, you know, you have formulas for surface area and other awful things. And you know, they do their best in calculus, but it's not elegant. And linear algebra just is, well, you know, linear algebra is about the nice part of calculus, where everything's like flat. And the formulas come out right. And you can go into high dimensions, where in calculus, you really, you know, you're trying to visualize these things. Well, 2 or 3 dimensions is kind of the limit. But here we don't, you know, I've stopped doing 2 by 2s. I'm just talking about the general case. Okay, now I really will speak about the general case here. What could be the inverse? What's a kind of reasonable inverse for a matrix, for the completely general matrix where there's a rank R, but it's smaller than n, so there's some null space left, and it's smaller than m, so A transpose has some null space, and it's those null spaces that are screwing up inverses, right? Because if a matrix takes a vector to 0, well, there's no way an inverse can, like, bring it back to life. So now my topic is now the pseudo-inverse, and let's just by a picture see what's the best inverse we could have. So here's a vector x in the row space. I multiply by A. Now the one thing everybody knows is you take a vector, you multiply by A, and you get an output, and where is that output? Where is AX? Always in the column space, right? AX is a combination of the columns. So AX is somewhere here. So I could take all the vectors in the row space. I could multiply them all by A. I would get a bunch of vectors in the column space. And what I think is I'd get all the vectors in the column space just right. I think that this connection between an x in the row space and an AX in the column space, this is 1-to-1. There's exact, I mean, well, look, we got a chance because they have the same dimension. That's an R-dimensional space, and that's an R-dimensional space. And somehow the matrix A, it's got these null spaces hanging around where it's knocking vectors to 0. And then it's got all the vectors in between, which is almost all vectors. Almost all vectors have a row space component and a null space component. And it's killing the null space component. But if I look at the vectors that are in the row space with no null space component, just in the row space, then they all go into the column space. So if I put another vector, let's say y, in the row space, I am positive that wherever ay is, it won't hit ax. You see what I'm saying? Let's see why. All right, so here's what I said. If x and y are in the row space, then ax is not the same as ay. They're both in the column space, of course, but they're different. That would be a perfect question on a final exam, because that's what I'm teaching you in that material of Chapter 3 and Chapter 4, especially Chapter 3. If x and y are in the row space, then ax is different from ay. And so what this means is that, and we'll see why, what this means is that in words, from the row space to the column space, A is perfect. It's an invertible matrix. If we like limited it to those spaces. And then its inverse will be what I'll call the pseudo-inverse. So that's what the pseudo-inverse is. It's the inverse. So A goes this way from x to y, x to ax, from y to ay. That's A going that way. Then in the other direction, anything in the column space comes from somebody in the row space, and the reverse there is what I'll call the pseudo-inverse, and the simple notation accepted notation is A plus. So y will be A plus x. Y will be A plus times whatever it started with, ay. Do you see my picture there? Same, of course, for x and ax. This way, A does it. The other way is the pseudo-inverse. And the pseudo-inverse just kills this stuff, and the matrix just kills this stuff. So everything that's really serious here is going on in the row space and the column space. And now tell me, so this is the fundamental fact, that between those two r-dimensional spaces, our matrix is perfect. Why? Suppose they weren't. Why do I get into trouble? So proof. I haven't written down proof very much, but I'm going to use that word once. Suppose they were the same. So these are supposed to be two different vectors. Maybe I better make the statement correctly. If x and y are different vectors in the row space, maybe I'll better put if x is different from y, both in the row space. So I'm starting with two different vectors in the row space. I'm multiplying by A. So these guys are in the column space. Everybody knows that. And the point is, they're different over there. So suppose they weren't. Suppose AX equals AY. Suppose, well, that's the same as saying AX minus Y is 0. So what? So what do I know now about x minus y? What do I know about this vector? Well, I can see right away. What space is it in? It's sitting in the null space, right? So it's in the null space. But what else do I know about it? Here was x in the row space, y in the row space. What about x minus y? It's also in the row space, right? Heck, that thing is a vector space. And if a vector space is anything at all, if x is in the row space and y is in the row space, then the difference is also, so it's also in the row space. So what? Now I've got a vector x minus y that's in the null space, and that's also in the row space. So what vector is it? It's the 0 vector. So I would conclude from that that x minus y had to be the 0 vector. X was y. So in other words, if I start from two different vectors, I get two different vectors. If these vectors are the same, then those vectors had to be the same. That's like the algebra proof, which we understand completely because we really understand these subspaces, of what I said in words, that a matrix A is really a nice invertible mapping from row space to column space. If the null spaces keep out of the way, then we have an inverse. And that inverse is called the pseudo-inverse, and it's very, very useful in applications. Statisticians discovered, oh boy, this is the thing that we needed all our lives, and here it finally showed up. The pseudo-inverse is the right thing. Statisticians, why do statisticians need it? And because statisticians are like least squares happy. I mean, they're always doing least squares. And so this is their central linear regression. Statisticians who may watch this on video, please forgive that description of your interest. One of your interests is linear regression and this problem. But if this problem is only okay provided we have full column rank. And statisticians have to worry all the time about, oh, God, maybe we just repeated an experiment. You know, you're taking all these measurements. Maybe you just repeat them a few times. Maybe they're not independent. Well, in that case, that A transpose A matrix that they depend on becomes singular. So then that's when they needed the pseudo-inverse. It just arrived at the right moment, and it's the right quantity. Okay. So now that you know what the pseudo-inverse should do, let me see what it is. Can we find it? So this is to complete the lecture is, how do I find this pseudo-inverse A plus? Okay. Okay. Well, here's one way. And everything I do today is to try to review stuff. One way would be to start from the SVD, the singular value decomposition. You remember that factored A into an orthogonal matrix times this diagonal matrix times this orthogonal matrix. But what did this diagonal guy look like? This diagonal guy, sigma, has some non-zeros. And you remember they came from A transpose A and AA transpose. These are the good guys. And then some more zeros, and all zeros there, and all zeros there. So you can guess what the pseudo-inverse is. I just invert stuff that's nice to invert. Well, what's the pseudo-inverse of this? That's what the problem comes down to. What's the pseudo-inverse of this beautiful diagonal matrix? But it's got a null space, right? What's the rank of this matrix? What's the rank of this diagonal matrix? R, of course. It's got R non-zeros, and then it's otherwise zip. So it's got n columns, it's got m rows, and it's got rank R. It's the best example, the simplest example we could ever have of our general setup. Okay, so what's the pseudo-inverse? What's the matrix? So I'll erase our columns because right below it I want to write the pseudo-inverse. Okay. Okay, you can make a pretty darn good guess. If it was a proper diagonal matrix, invertible, if there weren't any zeros down here, if it was sigma 1 to sigma n, then everybody knows what the inverse would be. The inverse would be 1 over sigma 1 down to 1 over. But of course, I'll have to stop at sigma r. And it'll be the rest zeros again, of course. And now this one was m by n. And this one is meant to have a slightly different, transposed shape, n by m. They both have that rank r. What is, so my idea is that the pseudo-inverse is the closest I can come to an inverse. So what is sigma times its pseudo-inverse? Can you multiply sigma by its pseudo-inverse, multiply that by that? What matrix do you get? They're diagonal, rectangular, of course. But of course, we're going to get 1s, R1s, and all the rest zeros. And the shape of that, this was m by n. This whole matrix will be m by m. And suppose I did it in the other order. Suppose I did sigma plus sigma. Why don't I do it right underneath? What in the opposite order? See, this matrix hasn't got a left inverse, it hasn't got a right inverse, but every matrix has got a pseudo inverse. If I do it in the order sigma plus sigma, what do I get? Square matrix, this is m by n, this is n by m. My result is going to be m by m, is going to be n by n. And what is it? Those are diagonal matrices. It's going to be 1s and then zeros. It's not the same as that. It's a different size. It's the projection. It's a projection matrix onto, one is a projection matrix onto the column space, and this one is the projection matrix onto the row space. That's the best the pseudo-inverse can do. So what the pseudo-inverse does is, if you multiply on the left, you don't get the identity. If you multiply on the right, you don't get the identity. What you get is the projection. It brings you into the two good spaces, the row space and column space. And it just wipes out the null space. So that's what the pseudo-inverse of this diagonal one is. And then the pseudo-inverse of A itself, this is perfectly invertible. What's the inverse of V transpose? Just another tiny bit of review. That's an orthogonal matrix, and its inverse is V. Good. This guy has got all the trouble in it. All the null space this is responsible for. So we can't, it doesn't have a true inverse. It has a pseudo-inverse. And then the inverse of U is U transpose, thanks. Or, of course, I could write U inverse. So that's the question of how do you find the pseudo-inverse? So what statisticians do when they're in this, so this is like the case of where least squares breaks down because the rank is, you don't have full rank, but the beauty of the singular value decomposition is it puts all the problems into this diagonal matrix where it's clear what to do. It's the best inverse you could think of is clear. You see, there could be other, I mean, we could put some stuff down here. It would multiply these zeros and wouldn't have any effect, but the good pseudo-inverse is the one with no extra stuff. It's sort of like as small as possible. It has to have those to produce the ones. If it had other stuff, it would just be like it would be a larger matrix. So this pseudo-inverse is kind of the minimal matrix that gives the best result, sigma, sigma plus being R1s. Okay. So I guess I'm hoping pseudo-inverse again. Let me repeat what I said at the very beginning. This pseudo-inverse, which appears at the end, which is in section 7.4, and probably I did more with it here than I did in the book. I'm not, the word pseudo-inverse will not appear on an exam in this course, but I think if you see this all will appear, because this is all what the course was about, chapters 1, 2, 3, 4. But if you see all that, then you probably see, well, okay, the general case had both null spaces around, and this is the natural thing to do. Yeah. So this is one way to find the pseudo-inverse. The point of a pseudo-inverse, of computing a pseudo-inverse, is to get some factors where you can find the pseudo-inverse quickly, and this is like the champion. Because this is one where we can invert those two easily just by transposing, and we know what to do with the diagonal. Okay, that's like as much review maybe. Let's have a 5-minute holiday in 1806, and I'll see you Wednesday then for the rest of this course. Thanks.